So we defined a maximal ideal last time. A proper ideal in a commutative ring R, and all rings are all these commutative rings are assumed to always have identity, is called a maximal ideal if there is no proper ideal of R that properly contains this ideal. So if you have R and you have M, if you get a I which is bigger than M, then it better be all of R. There is nothing strictly in between. Note that this does not mean that M is like the biggest ideal or anything. It's maximal. In particular, there could be many maximal ideals. And this lemma that we proved is how you recognize a maximal ideal. An ideal M in R is maximal if and only if when you quotient by it you get a field. And that essentially follows from the lemma up here. That fields are exactly the commutative rings with one that have no proper ideal whatsoever. So you just have 0 and R. And the proof of this other lemma is that you have R and M. Now you quotient by M, then you go to R mod M, and M becomes the 0 in this ring. And the ideals in between here will correspond to the ideals in between here. That's the correspondence theorem. So R mod M is a field means that there is nothing in between here, which means there is nothing in between here, which means M is maximal. On the other hand, if M is maximal, then there is no ideal in between here. That means there is no ideal in between 0 and R mod M. That means R mod M is a field. That's a quick recap of the proof of this. Okay. So what I want to do is use this to give some examples. But first, I think it will be convenient if we do this little exercise. Let f be a field, and let's take the two variable polynomial ring. So for f, you can take rational numbers or real numbers or complex numbers or something. Verify that there is a surjective ring homomorphism from the two variable polynomial ring R to the one variable polynomial ring Fy defined by f of xy equals f of f of xy mapping to f of 0y. So they substitute x equals 0, then you get a one variable polynomial in y. And this is a surjective ring homomorphism. And the kernel of this homomorphism, let's call this guy alpha. So alpha of fxy is f of 0y. And the kernel of alpha is generated by x, meaning all multiples of x in R. So polynomials that look like f times a two variable polynomial. Yeah, that's what this means. All polynomials that look like that. So by first isomorphism theorem, if you have a surjective homomorphism from R to Fy with kernel being this thing, so R mod the kernel, remember, is the image. Okay, so that's another quotient ring that you identified. Here's another one. Verify that there is a surjective ring homomorphism called evaluation at 0, or maybe at 0, 0, from R to F, the field defined by evaluation at 0, 0. So you give me a two-variable polynomial, and the homomorphism, what it does is it evaluates that two-variable polynomial at 0, 0. And check that the kernel of this guy is the ideal generated by x and y. So all polynomials that look like x times x fxy plus y times gxy. Yes, another way to describe this ideal would be all two-variable polynomials that have no constant term. Okay. And check that. It's the same as this, where f g vary over r equal to set of all elements of R with 0 constant term. In any case, because this ideal is the kernel of this evaluation homomorphism, again, and the evaluation homomorphism is a surjective ring homomorphism, again by first isomorphism theorem, what I get is that the domain ring mod the kernel is isomorphic to the image. And I didn't want to do these exercises one by one, so these exercises are basically the reason why we introduced this big lemma down here last time. Yeah, if you do this, and then you get all these little things for free. Okay. Or you can just check by hand also. Okay. All that you have to basically verify that this is both these things are ring homomorphisms. Like the second one you have already done before, I think. And the first one is also almost completely tautological. And the fact that they are onto is completely visible as well. But once this is less of an exercise, more of just an observation. Once you know this, I can give some examples. Better be visible. So you take R equals fxy, where f is a field. Then you see that R mod x is fy. And the one variable polynomial ring is certainly not a field. Okay, the only units in one variable polynomial ring over a field are the constants, and there are plenty of non-constants like y and y square, etc. This is not a field, so by the lemma, this is not a maximal ideal. But then if you take R mod xy, that we just said is isomorphic to f, that was part B. That is a field. So xy is a maximal ideal. Another one would be something like x minus 1, y minus 2. you can check that this is the kernel of the evaluation at 1, 2. Instead of evaluating at 0, 0, you can evaluate at 1, 2, and that also gives you a surjective homomorphism from R to the field F. So these are some maximal ideals in the two-variable polynomial ring. Maximal ideals in one-variable polynomial rings would be exactly the prime ideals generated by irreducible polynomials. This we'll prove a little later. You can check at least that fx mod x, for example, is just f. So by the same way you checked this one. So x is maximal in f. Maybe even before that we should look at z. So here are some ideals in z. So this one, 6z, is not maximal. Well, you can say it in two ways. One way would be to note that here is a strictly bigger ideal. Multiples of 3 is a strictly bigger set than multiples of 6. So there is a strictly bigger ideal between 6z and z, so 6z is not maximal. Or you could say that if you take z mod 6z, that's not a field. On the other hand, 3z is maximal since z mod 3 is a field. So the maximal ideals in Z are pz, where p is a prime number. Okay, well, this is a little misleading because we'll define prime ideals next, and in Z and in one variable polynomial ring, and the prime ideals and the maximal ideals happen to be the same. But these are not identical concepts, so that's why I first wanted to focus on these examples where the notions actually are different notions. Okay. So next we'll recall a little bit about principal ideals and talk about divisibility and then get to prime ideals.